Hey, so we're going to start in just a few minutes. We're done the recording. So we're going to be doing some more on power series today. And I've got this warm-up problem. So take a few minutes, check it out, and then we're going to talk about it in just a few. Okay. If you remember, this problem is actually from the previous homework. So I just kind of want to go over it and talk about testing endpoints, especially. So let's go ahead and get started. So when doing something like this, we can use the root or the ratio test. And we're going to go ahead and use the ratio test for this guy. So we're going to set the L to the limit as n goes to infinity of the absolute value. And then we're going to have the an plus 1 term. So here we've got 2n plus 3. And the bottom, n plus 1 to the 3 halves. And this is going to be multiplied by reciprocal of an, x minus 5, 2n plus 1, absolute value. So now we're going to have the limit here as n goes to infinity. And you'll notice here that we've got this 2n plus 3 and this 2n plus 1. So two of them are going to be left from this cancellation. Okay. So we've got absolute value for x minus 5 squared. And then n over n plus 1 to the 3 halves. Now, the x portion, this 4x minus 5 squared, has nothing to do with the limit, right? Because the limit's just n. So we're going to go ahead and pull that out. And by dominance of powers, that limit's going to be 1. So we're just left with 4x minus 5 squared. Now remember that we need this to be less than 1, right? So if we take the square root of both sides, we'll get the absolute value of 4x minus 5 is less than 1. Now, a few of you said that the radius here is 1. Well, that's not quite right, because remember, the definition of the radius is actually the absolute value of x minus a. And then we have r here. So we don't quite have it in that form, right? So we're going to need it in that form. So what we can do is factor out of 4. And then divide 4 over. So our radius is actually 1/4. Right? So now for the interval of convergence, we've got this negative 1/4 x minus 5/4, and then positive 1/4. Then we add 5/4 to each side. We get 1 and 3/2. Okay, so now that we have this interval of convergence, we're still going to need to find these, or check these endpoints, right? So endpoints. When x is 1, we have the sum from 1 to infinity of negative 1 to 2n plus 1 over n 3/2. And if you look at the quantity 2n plus 1, so we're multiplying n by 2, and if n is even and you multiply it by 2, it's still going to be even. And if you multiply it an odd number by 2, it's actually still even, right? So, and then we're adding 1, so this quantity is always odd, right? So now, this is the same thing as just negative 1 into the 3/2. And if you pull out a negative 1 out of this, this looks exactly like a p-series, right? And that converges. So that actually converges absolutely, right? So this is absolutely convergent. So now when x is 3/2, our sum equals 1 to infinity is now 1 to 2n plus 1 over n to the 3/2. And just like above, this is going to be a p-series. This is absolutely convergent. So that means that both endpoints are absolutely convergent. Now we've got our interval of convergence is 1 3/2, including 1 and 3/2, and our radius is 1/4. Right? Okay. Move on to the next page, and we're going to have number 2, and we're going to have the sum m equals 1 to infinity of x to the 2n over negative 3 to the n. Notice that these two problems have this 2n plus 1 and this 2n. It's not unlike power series to have these kind of powers of n. Remember, the definition was kind of just with the power of n. This just means that it skips every other turn. So you could rewrite this series as more complicated version that just has zeros in every other spot. So we kind of look at how this is defined. Like the first few terms, we've got x squared over negative 3 to the first, and then x to the fourth, negative 3 squared, x to the sixth, negative 3 third, and then so on. Right. So let's find the radius and interval of convergence. So why don't you guys go ahead and start, and then we'll talk about it in just a few minutes. Okay, so for this problem, see these powers of n, the numerator and the denominator both share. So the root test is a good place to start. So root test. And we're going to define L to being the limit n goes to infinity. And then we're going to have absolute x to the 2n over negative 3 the n power of 1 over n. This is the limit as n goes to infinity of just x squared over negative 3. Notice that there's no n's anymore. This is just x squared over 3. And we have to have this less than 1, right? So this means that x squared is less than 3. And then we have that the absolute value of x is less than radical 3. And this is our radius. Notice that it's centered around 0, because our a here is 0. So it looks like our interval before we check endpoints looks something like this, right? Negative radical 3 to radical 3. So let's check those endpoints. So when we have that x is equal to negative radical 3, our sum is this negative radical 3 to 2n over negative 3 to the n. So notice that since we've got this 2n, I'm going to square what I've got in there and then just have the exponent be n. Right? So this is 3n on top, right? And then what I'm going to do on the bottom is, since it's negative 3 to the n, I'm going to break that up into negative 1 to the n and 3 to the n. Well, those 3 to the n's are going to cancel. And if we've got 1 over negative 1 to the n, well, that behaves exactly like negative 1 to the n, right? And by the test for divergence, this guy diverges, right? Because it just goes between negative 1 and 1. So the limit doesn't exist. So we have that this guy diverges. Now, when x is radical 3, we have the sum from 1 to infinity of radical 3 to the 2n over negative 3 to the n, right? And this is going to be, believe it or not, this is going to be the same deal. And this also diverges. So our interval of convergence is just that, right? We can't include the bounds because they both diverge. Okay? So this is useful, right? These power series, but what do we really use them for? Well, if you remember back a few sections ago, we had a pretty well-known series the sum of from 0 to infinity of a Rn. Writing this out, we've got a plus a bar plus ar squared, and then so on. This is the geometric series, right? And we knew that that converged to we knew that this converged to a over 1 minus r, right? As long as we had that r was less than 1, the magnitude of r, right? Well, this is a power series, and it describes a function. So why don't we look at a more specific case where we have n equals 0 to infinity x to the n, right? Well, here a is 1, right? So this is just 1 plus x squared, and so on, right? Well, if we plug in what we knew about the geometric series, right? It's 1 over 1 minus x, for as long as x is less than 1. Well, think of it vice versa. We're not describing this sum as this guy, but the other way around. We're describing this function as a power series, right? As long as x is in this range, right? So that's the whole point of power series, is now writing functions as their power series, and we can manipulate them in that way. You'll see in later sections why they're really useful. So we have number 3 here. So let's prove why we had that interval of convergence, right? And this one's pretty easy, right? We have L defined as the limit as n goes to infinity, x to the n plus 1 over x to the n. And so we're going to have one x left over, and the limit, there's no n's left. So that's the absolute value of x. And guess what? Has to be less than 1. Right? And if we plug in those endpoints, we'll get either a plus or a minus 1, and that's raised to the n. And those both diverge. By the test for divergence, we take the limit of those things. That's where the interval of convergence comes from for that problem. Okay. So let's go ahead and look at our next example, number 4. We've got g of x, and it's equal to 1 over 1 plus x to the third. So now, let's find the power series of this function. As well as its radius and interval of convergence. Take a few minutes, and then we'll talk about it. Okay. So, with this problem, we have 1 over 1 plus x cubed. Now, we do know about the power series of 1 over 1 minus x. This is the sum n equals 0 to infinity of x to the n, right? So let's see if we can use that at all. If we have 1 over 1 plus x cubed, well, that's the same thing as saying 1 over 1 minus negative let me do an extra parentheses here. So you'll see what I'm talking about. So notice that in this guy, in this first line, we have this quantity 1 over 1 minus quantity x, right? Well, in this guy, we have, instead of this quantity, we have this quantity. And if we just plug that in, so g of x is equal to the sum equals 0 to infinity. And I'm going to plug that quantity in here. We have negative x cubed to the n. Well, this is, we simplify it a bit here. Negative 1 to the n. And an x to 3n. So this is our power series for g of x. So let's find its radius and interval of convergence. So our limit here, let's go ahead and do ratio. Negative 1 to the n plus 1, x to the 3n plus 3, all over negative 1 to the n, and x to the 3n. Notice that these negatives aren't going to mathematically be this absolute value. And then we have x to the 3n plus 3 and x to the 3n. So those 3n's are going to cancel. We're going to be left with 3. So we've got the absolute value of x cubed, right? And this has to be less than 1. Well, if we took a cube root on both sides, we would get that the absolute value of x is less than 1. And if you went ahead and plugged in the n bounds of negative 1 and 1 into our power series, you would see that all we would have is the negative 1 to the n, or just 1s all the time. And those are both going to diverge, just like how we had in this example down here, right? So we have the same interval of convergence and r for this power series. So what about the power series for h of x, which is 2x squared over 1 plus x to the third? All right, so this is a little bit more complicated. What is the power series of this function? So work on it for a few minutes and we'll talk about it. All right. So we have h of x is equal to this 2x squared over 1 plus x cubed. And it's a little bit more complicated than what we had before, because now the numerator has this factor of this 2x squared. Well, we found power series for number 4 by relating it to the geometric, right? And we found the power series for this 1 over 1 plus x cubed. And this kind of looks like the same thing. So there might be a way to manipulate this to look like this. And in fact, that's what we're going to do. We're going to set this equal, well, it is equal, right? So we've got 2x squared times 1 over 1 plus x cubed. Now, we knew, or we have found what the power series for 1 over 1 plus x cubed was, right? This power series right here. So, with that same logic, this should be 2x squared times the power series. Right? So let's also note that this power series had the condition that the absolute value of x had to be less than 1. Well, what is this really contributing? What is this doing by multiplying by this 2x squared? Well, regardless of what x was going to be, this is just a finite thing, right? This 2x squared. As long as x is finite, we have that the outside is finite. So if we have that this sum converges because of this condition, right? So x is already less than 1, or the absolute value of x is less than 1. And we have this quantity, as long as x is not infinite, it's just a finite number. So we have a finite number times a finite number. This means that this multiplication on the outside does not impact the interval of convergence for this, for the radius of convergence, right? So we're going to have the same r here, and we can rewrite this bringing the 2x squared inside. So now we're going to have 2 times negative 1 to the n, and then we have x, the 3n plus 2. And we still have the condition that the absolute value of x is less than 1. So we now have the power series for h of x. So later on, you're going to have to find power series that might be even a little bit more complicated than these things. So it's really good to do it in steps. So let's say we started with h of x, right? And we noticed that we could separate the numerator, and then we've got this thing that behaves a lot like the geometric. So if we weren't given 4 initially and we just had 5, it might have been a good idea to start doing this, find the power series for what we had in blue, and then go ahead and do the whole thing. So let's say that we had an additional term up here. Maybe this had an addition, and then we could separate into 2 different sums and found their power series and then add them together. So it might be something like that. So always kind of keep in mind that you want to get something back to the terms of the geometric, right? Because this is the geometric series is the one that we know how to do, right? We know already what its function is and what its power series is. Right? Later on, we're going to learn how to get to the power series of other functions, like sines and cosines. And that's one of the best parts of Calc 2. So let's look at what happens if we take derivatives of these things, right? So let's say that we've got some function. Oops, I got my highlighter. So we've got some function x, and this is equal to the sum from 0 to infinity. We have the coefficient Cn, and then we have x minus a, so the power series centered around a. And now we have the condition that r is greater than 0, meaning that it doesn't just converge when x is a, but it converges for a larger radius. So it has an interval of convergence that's not just a. Right? If this is true, then what do we have for the derivative of x? Well, let's take a look at f of x expanded out. So let's write out the first few terms. So we've got c0, then we've got c1 times x minus a. Then we've got c2, x minus a squared. Then we've got c3, x minus a to the third, and so on, right? And this is just a polynomial that goes on forever. So if I take a derivative, so I've got d dx of this function, well, it's d dx of c0 plus c1 x minus a plus c2 x minus a x minus a squared here. And then we have c3 x minus a cubed, right? And so on. Well, the derivative can apply to each one of these, right? We know how derivatives behave. And if that's the case, then the derivative of the first term is 0, right? We've got 0. Now, the next term is the c1 times x minus a, right? And if we take the derivative of that, we're only going to get c1. Now, if we look at the second term, we've got c2 times x minus a squared. So when we do the derivative, that 2 is going to come down. We're going to get a c2, and then an x minus a, just like power rule, right? And then we have a power of 1. If we look at the next term, a 3 is going to come down, and we're going to get c3 x minus a squared, and then so on. Well, we can rewrite that as a sum, right? So we write it out formally. We have that the derivative of x is then the sum. And notice that our very first term, c0, is 0. So we're not going to include it. So we're going to start at 1 instead of 0, okay? And then we're going to infinity. And now notice that it's c is in each one, so we've got cn, but we also now have these 2s and 3s that show up. And there's, of course, going to be a 4 in the next one. So in our sum here, we're going to have n times Cn times x minus a to the n minus 1, right? And that's going to be our derivative. Likewise, let's talk about integrals. What happens if we took an integral of this sum? So what is the integral of f of x dx? Right? Well, back up here, we had our f of x, right? C0 plus C1, x minus a, and so on. Well, if we look at this and apply the same kind of logic that we did here, if we took an integral of each one of these, we should be able to get the integral of the power series, right? So if we look at this first one, we're going to get an x, right? Divided by 1. And then this next one, this power is going to go up, right? We're going to have a power of 2, right? So it turns out we can do that. And the power series for the integral of f is going to be some constant, right? Because it's an indefinite integral. So we're going to have some kind of constant, c. Now the sum, n equals 0 to infinity, our cn's, x minus a to the n plus 1. And then on the bottom, we're going to have n plus 1, right? And now this is our definition for integrating a function who has a power series. Now, it's really interesting to note here that if we had some r, right, this r, the r for f prime of x and the integral for f of x dx are the same as just f of x. So this r here is the same r for the power series that we had for f of x. So that's really helpful. All right, so let's go ahead and start looking at an example. I'm going to go to the next page. We've got number 6 here. Oops, still have the highlighter. 6. So we have g of x. And we're going to set this equal to 1 over 1 minus x squared. So what is the power series of g of x? I'm going to give you guys a few minutes, and then we'll talk about it. Okay, so we have g of x is equal to 1 over the quantity 1 minus x squared. So if we kind of look at this and realize that this is actually equal to d dx of 1 over 1 minus x, right? And this is a sum that we know how to do, or the power series of, right? This is our geometric. So, back to our problem, we can rewrite this line here as d dx, and now I'm going to input our power series here from 0 to infinity of x to the n. And we know from the last page here what actually happens when we take a derivative, right? We're going to get this n, we're going to have this coefficients, and then we're going to have x minus a and this n minus 1. Don't forget that we're moving up an index, right? So we can write this as the sum as n equals 1 to infinity n x to the n minus 1. And again, because r was 1 in the geometric series, we have the same r here, right? Okay, so that leads us to our next problem, number 7. We have h of x, and this is equal to the natural log of 5 minus x, right? What is the power series of h of x? So I'm going to give you guys a few minutes, and then we're going to talk about it. This one's a little bit more complicated. It's actually got kind of 2 steps in it. So it's applying some of the things that we've learned with derivatives and integrals, and also just manipulations. So give it a go, and we'll talk about it. Okay, so we have the natural log of 5 minus x. Well, if we have the integral of 1 over 5 minus x dx, this is negative natural log of 5 minus x, right? So we have something similar to h of x, only differing by this minus sign, which isn't too much of a deal. So, but now we've got this 1 over 5 minus x, right? And that's not quite the geometric series. We have 1 minus over 1 minus x. So let's take a look. Let me just highlight that for a second, and we'll look at it in just a bit. So we have this 1 over 5 minus x. Well, that's kind of like this pulling a 5 out here, right? And this is 1/5 times 1 over 1 minus x over 5. Well, we can plug in that x over 5 into the geometric series, right? So we have 1/5, and then the power series. Right? You can move that 1/5 inside. And now we've got x to the n over 5 to the n plus 1. Right? So now we have our power series for 1 over 5 minus x. So remember, we also have this negative here. Okay? So if I take negative times the integral of this power series, I should be able to get the power series for h of x. So now this is, remember there's a negative, so I'm going to have this big constant out here. And I'm not going to put a negative in front of it because I don't know what it is, so I'm just going to keep it as big C. Right? So the negative can be absorbed into it. N equals 0 to infinity of x to the n plus 1. And then we're going to have an n plus 1 down here, and a 5 to the n plus 1. So we're not quite done yet, right? We can actually find out what c is, because remember, this supposedly is equal to the natural log of 5 minus x, right? So I say that the natural log of 5 minus 0, well, this is big C minus the sum here, n equals 0 to infinity. And I plug in 0, so I've got 0 to the n plus 1 all over n plus 1, 5 to the n plus 1. Well, that's just adding zeros, right? So that whole sum is going to be equal to 0. So this is just equal to c. And from before, we knew that this is the natural log of 5. So putting it all together, we've got that h of x is equal to natural log of 5 minus the sum from 1 to infinity of x to the n minus 1 all over n plus 1, 5 to the n plus 1, right? And there's no way to move that natural log inside, so don't worry about it too much. It's just going to be this constant that's just going to float around outside of it. But this is still our power series for h of x. All right, so that concludes all of our example problems. I hope you guys learned something. Definitely know how to manipulate these power series, right? This is very important because power series is basically the basics for some of the other things we're going to be learning. We're going to be learning about Taylor series expansions. And what Taylor series expansions are is power series for functions that use derivatives as coefficients. So the coefficients for these power series, these CNs, are defined with derivatives, with nth derivatives. And there's some other factors there that we'll talk about next time. But what that does is take polynomials and makes like a best fit curve with all these additional terms that keeps getting closer and closer to the real function as you add terms, right? So that's kind of cool, right? Like think of the sine and cosine curves, and then think about trying to match that with polynomials, right? So that's what we're actually going to be talking about next time. So I hope you guys join for that recitation. And I will see you guys next time. All right, take care.